So we are back to our chapter 4 integration land of antiderivatives. And so with that being said, we are going to jump into 4.3, which talks about something called definite integrals. Okay, so do tricky integration worksheet. Homework is problem set 4.3, which is posted on WebAssign. Calc Lecture will be linked when it is obviously done. So part 1. Definite and indefinite integrals. So we're going to start with what we know. And what we know is indefinite integrals. All of the integrals that we have done thus far have been in the form of the integral of f prime of x dx equals f of x plus c. Getting at that idea that we start with the derivative and we can go backwards to the initial function using this thing called integration. And remember that we call f of x the integrand, I-N-T-E-G-R-A-N-D. dx is called the variable of integration. And that variable of integration has to match what variables in your integrand. And c is called the constant of integration. Okay. And when we take the integral of a problem, like the integral of f prime of x dx, we get a general solution. And that's because of that plus c at the end, which represents any and all constants, right? It's a general solution because when you take the integral and add plus c represents generally anything, okay? So that's a general solution. However, if we solve for c, then that takes us to what we call a specific solution. And we can find a specific solution when we are given information about the problem. So, for example, find a solution to f prime of x equals 4x minus 3, given that f of 1 is equal to 2. So first, we want to find the antiderivative. So the integral of 4x minus 3 dx is going to be equal to 4 times the integral of x dx. Remember, we can break apart integration at addition or subtraction signs, minus 3 times the integral of dx. And remember, we can also pull out constants, such as 4 and 3. 4 times the integral of x is going to be 4 times x squared over 2. And I have now dropped that integral sign, that long s thing, because at this point I have taken the integral. Whenever you apply a rule, like x changed from x squared over 2, that means I've taken my integral, I need to get rid of that long s sign. Minus 3 times, remember the integral of dx is essentially the integral of 1. The integral of 1 is x. Think about that as the derivative of 3x is equal to 3. So, just creating some connections over here. And then we have to add c, right? Plus c, because this is a general solution. So first we find the antiderivative, which is going to be 2x squared minus 3x plus c. Okay, then we know that f of 1 is equal to 2. And so we're going to plug in 1 for x, this is our x value, and 2 for f. Okay, so now we know that the antiderivative is f of x equals 2x squared minus 3x plus c. And now we want to know that f of 1 is equal to 2. So we know that 2 is equal to 2 times 1 squared minus 3 times 1 plus c. So 2 is equal to 2 minus 3 plus c. 2 minus 3 is negative 1, so 2 equals negative 1 plus c. I'm going to add 1 to the other side, so I get 3 is equal to c. So such that c is equal to 3. Therefore, our particular solution, and it's called a particular solution when we have explicitly solved for that c, our particular solution is going to be f of x equals 2x squared minus 3x plus 3. The end. So it's like one extra step when we are given information about a function to get to that particular solution. Okay, and that kind of brings us into the next part of this, which is definite integrals. The definite integral looks exactly like an indefinite integral with one exception. A definite integral utilizes bounds with a starting and ending point. a definite integral takes the following form. The integral from a to b, so we now have letters at the end, a to b, of f of x dx, where f of x is still the integrand, dx is still the variable of integration, but a has now become the lower limit of integration and b is the upper limit of integration. I'm not going to write out that whole thing. The difference between definite integrals and indefinite integrals is simply that definite integrals have a defined starting and ending point. And this idea of definite integrals brings us to the fundamental theorem of calculus. Sounds like a really big deal, like the fundamental theorem, which it is. It's pretty big deal. So basically the fundamental theorem of calculus, it was what allows us to evaluate definite integrals, okay? And so if we have a function that is continuous on a closed interval, then the integral from a to b of f prime of x dx is equal to f of b minus f of a. So this is saying that we take our integral as normal and we go from f prime of x to f. So f prime of x to f of x, right? So from the derivative to the initial function, except for now, when we get that initial function, we're going to be plugging in numbers and we're going to plug in the top f of b minus the bottom f of a. Okay, so where f is any function such that the integral of f of x, f prime of x dx, yikes, Miss Hogan, dx is always needed, equals f of x for any x in the interval. Okay, so we're going to do some examples of these definite integral problems. Okay, so let's start out with the number one, right? So we have the integral from 1 to 2 of x squared minus 3 dx. Okay, so first thing we're going to do is evaluate our integral completely normally. Okay, we know that the integral of x squared minus 3 dx is going to be equal to x cubed over 3 minus 3x, okay? That's just using our basic rules, splitting the integral along the subtraction sign. By this point, you should be pretty comfortable with that. And then what we're gonna do is we're gonna draw this line, and remember that line means evaluated from. So we have x cubed over 3 minus 3x evaluated from, and now we plug in our bounds, 1 to 2, okay? And you can write 1 and 2, or you can even write it even a little bit fancier here, and you could write x equals 1 to x equals 2. So we could also do from x equals 1 to x equals 2. I usually don't write x equals, I guess, just saving time or something. I don't know. Maybe I should start doing that. Okay, and now what you do is, again, plug in your top bound and then your bottom bound, okay? So, I'll color code this. So we are going to have x equals 2. Didn't mean to do that. So x equals 2. So we're going to plug in 2 to our function. So we're going to have 2 cubed over 3 minus 3 times 2. That's f of b minus, now we want f of a, and our a is 1. So 1 cubed over 3 minus 3 times 1. And that is it. Now we evaluate that and figure out that we should end up getting negative 2/3. So 2 cubed is 8/3 minus 6 minus 1/3 minus 3. So 8/3, that's going to be 8 over 3 minus 18 over 3 minus 1/3 minus 9/3. Okay, so then you're going to get 8 minus 18 is negative 10/3 minus 1 minus 9 is going to be negative 8/3. So you're going to get negative 10/3 plus 8/3 is equal to negative 2/3. Okay, so I was right. Negative 2/3. Okay, let's do another example. So number 2, we have the integral from 1 to 4 of 3 times the square root of x dx. Okay, and so we are going to take our integral normally. So 3 times the integral of x to the 1/2 dx is going to give me 3 times 2x to the 1 to the 3 halves, 2x to the 3 halves, plus c. Again, that is just our normal integration, nothing fancy there. So then, or no, I did that integral wrong. So it's going to be 3 times, I tried to do too many steps in my head. Don't do that. So 1/2 plus 1 is 3 halves. So it's going to be 2/3 x to the 3 halves. Evaluated from 1 to 4. And these 3's are going to cancel. So we're going to get 2x to the 3 halves from 1 to 4. And then we're just going to plug and chug. 2 times 4 to the 3 halves minus 2 times 1 to the 3 halves. And then we are going to get 14 for this one. Okay. Number 3, I will let you do on your own, but you should get equals to 51 halves. And then if we need to go over that in class, we can do that. And then number 4, is also not super tricky, and so we can go over that in class, but the answer you should get is -39/2. Okay, so again, remember your steps. You just want to evaluate your integral normally and then go from your upper bound minus your lower bound. You just kind of plug it in, do a little bit of algebra. Okay. Part 3, definite integrals with the absolute value function. So the absolute value graph is really a piecewise function. So we're going to draw that out. So here's my axes, and here is my absolute value graph. That was actually a really nice one. Y is equal to the absolute value of x, okay? And this can be defined as the piecewise function, f of x equals the absolute value of x, which is equal to negative x when x is less than 0, right? So that's this part of the graph, which is negative x. And then it is equal to x when x is greater than 0. So in our positive x values, which is going to be this part of the graph over here, our function is x. Okay, so when we take the integral of an absolute value function, we need to integrate using portions to both the left or the right of the vertex. Okay, and so that means we need to use 2 integrals to solve the problem. So if c right here, right here, represents the vertex of the graph, then the integral from a to b of some absolute value function, whatever it is, absolute value of f of x, is going to be equal to the integral of the left bound to the vertex of negative f of x, right? We can see where that comes from. It's from this side of the graph, plus the integral from c to the right bound of f of x, just normal f of x right here, okay? So take a second, think about this, and we're going to do an example problem. So whenever you see absolute value function in an integral, you should automatically be thinking 2 integrals. And this is a really tricky, weird, niche type thing that AP would probably love to drill you on. So try to remember this, and we can do more problems. But okay, for instance, the integral from 0 to 3 of the absolute value of x minus 1 dx, okay? So where is the vertex of this function? The vertex of this function is at x equals 1, which you should know because of basic graph transformations, right? So we have the absolute value of x minus 1, that means it's shifted to the right 1. So we know that the vertex is going to be at positive 1, okay? And then looking at what we know above, let me not erase that, vertex of x equals 1, so right here, we're gonna look at this guy. So we know that we're going to have the integral from 0 to 3 of the absolute value of x minus 1 dx equal to the integral from a, so our lower bound is 0, to c, our vertex is 1, of negative f of x, so negative x plus 1 dx, plus the integral, and again, remember, if you're looking at this, we drop off our absolute value function, okay? So we have negative f of x, so negative x minus 1 is going to be negative x plus 1. So that's where this negative x plus 1 comes from, plus the integral from c, again, 1 to our upper bound, which is 3 of f of x dx. F of x is just x minus 1 dx. Okay, and so now we can evaluate those integrals and come to our final answer. Okay, so we have the integral of, this is going to be the integral from 0 to 1 of negative x plus 1. The integral of negative x plus 1 dx is going to be equal to negative x squared over 2 plus x evaluated from 0 to 1. And then over here, plus we have the integral, I'm going to draw like a dashed line down the middle because we're still adding these, but they're kind of separate in our brains. Plus the integral of x minus 1 dx is equal to x squared over 2 minus x from 1 to 3. Okay, and now we need to plug in. So I'm going to do some work over on the side of my pippa. So I have negative x squared over 2 plus x from 0 to 1. So I'm going to have negative 1 squared over 2 plus 1 minus negative 0 squared over 2 plus 0. So that's just going to be, this is all going to go to 0 minus 0. So it's going to be 1/2 plus 1, which is equal to 3 halves minus 0, which is just 3 halves. And then on my other side, I have x squared over 2 minus x from 1 to 3. So I'm going to have 3 squared over 2 minus 3 minus 1 squared over 2 minus 1. So 3 squared is 9 halves minus 3 over 2 is going to be 6 over 2 minus 1/2 minus 2 over 2. So 9 minus 6 is 3 halves. So I'm going to have 3 halves minus 1/2 minus 2 is going to be negative 1/2. So it's going to be 3 halves plus 1/2, which is equal to 4 halves, which is equal to 2. So I'm going to have, shoot, I might have made a mistake somewhere. I'm going to check my work in the green. Negative 1/2. When I plug in 1, I'm going to get negative 1 squared, which is 1/2 plus 1, which is equal to 3 halves minus, when I plug in 0, I get 0. Let me go ahead and, okay, so actually I'm going to go back in the green and check my work here. And it actually, that negative does not belong, I kind of wrote that in a confusing way. Oh, that should still be the eraser. So it's going to be negative out here, x squared. So negative 1, it's going to be, oh my gosh. Okay, try again. Negative 1 squared over 2 plus 1, or not all the way out there. It's still in there. But I'm going to get negative 1/2 plus 1 is equal to 1/2. So that's actually going to be 1/2. So then I get 1/2, and remember that I am doing addition here, right here, plus, and then on my other side, I got 2. So 1/2 plus 2 is going to give me 5 halves. So my answer for this integral would be 5 halves. And whenever you see that absolute value, you need to be breaking it up, figuring out where the vertex is, that sort of thing. Okay, so chugging right along, we have one more section, definite integrals and u substitution. So maybe back in part 2, you noticed that we were only taking the integral of basic functions. So we were looking at functions where we didn't need to use u sub to take the integral. But we know, unfortunately, that that is wishful thinking, right? So when we have a problem like the integral from negative 1 to 1 of 2x squared, or 2x minus 1 quantity squared in terms of x, we know that we are dealing with a problem that needs u substitution, okay? And so the important thing to note is that the bounds of this integral were set when we were integrating with respect to x. So these bounds are in terms of x. When we take the integral from negative 1 to 1 of 2x minus 1 squared dx, we will let u equal 2x minus 1, du equals 2 dx, dx equals du over 2. So this is going to be the integral of u squared times du over 2. It is not correct, I'm going to write it in red because it's not correct, to write the integral from -1 to 1 of u squared du over 2. Okay, and the reason for that is because the bounds were set in terms of x. And now that we're in terms of u, these bounds are no longer correct. We're dealing with a different variable. And so there are a couple of different ways that you can get around this. So I'll show you both and you can choose which way you like better. So you can first change the bounds of integration to represent working with u, okay? Or you can use some type of symbol, like a star, for the bounds until after you have performed u sub, and then your problem is back in terms of x. So remember, you do your u sub and then you plug u back in. So you get your function back in terms of x. So you can use something as a placeholder until your function is back in terms of x, in which case you can use the bounds that you have, okay? So I'm gonna use this number 2 method for now, but I will do another example that uses the first method, okay? So if we're looking at the integral from -1 to 1 of 2x minus 1 quantity squared dx, we know that u equals 2x minus 1, du equals 2 dx, dx equals du over 2. So now I'm going to rewrite my integral as the integral from star to star, because my bounds are no longer accurate, so I'm using star as a placeholder, of u squared times du over 2. I'm going to pull out that 1/2, so I'm going to have 1/2 times the integral of star to star, u squared du. The integral of u squared is going to be 1/2 times u cubed over 3. And then that is going to be equal to u cubed over 6, okay? And then I know that u was equal to 2x minus 1. So I'm going to have 2x minus 1 cubed over 6 evaluated from, now I can go back to my initial bounds, which is going to be -1 to 1, okay? And I'm going to let you guys get a little bit of practice of plugging that in, doing some work with fractions, but you should get 1/6 minus -9/2, which is going to equal 14/3. So that is what you should get for this problem, okay? And again, you use the stars as placeholders until you get back in terms of x right here, where we can go back to using our original bounds, okay? So that's one option. There is another option, and I'm going to do a different problem. I'm going to do the second one down, this guy right here, x plus 2 to the 5th. And I'm going to use this problem as an example of the other way to do it, okay? So I have the integral from 1 to 4 of x plus 2 to the 5th, the integral from 1 to 4 of x plus 2 to the 5th dx. Okay, so u is equal to x plus 2, du is equal to dx, okay? And now I'm going to rewrite my integral in terms of u, okay? So I'm going to have the integral of u to the 5th du. And now I'm going to change my bounds to be with respect to u. So I know that these bounds are x equals 1 to x equals 4. Now I need them in terms of u. Conveniently, I have an equation for u in terms of x, and that is going to be right here. U is equal to x plus 2. So for my lower bound, x equals 1, so u is equal to x plus 2, which is 1 plus 2 is equal to 3. So my lower bound in terms of u is going to be 3. And I'm going to put that right here. And then I need to figure out my upper bound. My upper bound is x equals 4. X equals 4. U equals x plus 2. 4 plus 2 equals 6. So my upper bound in terms of u is going to be 6. So I have the integral from 3 to 6 of u to the 5th du. The integral of u to the 5th is u to the 6th over 6 from 3 to 6. And so when you change your bounds, you don't ever have to go back and plug in u equals x plus 2. You can keep the whole thing in terms of u now. You are in the land of u's. Your bounds are adjusted and you are good to go. So you have u to the 6 over 6 from 3 to 6. So when we plug that in, that's going to be 6 to the 6th over 6 minus 3 to the 6th over 6. 6 to the 6th is going to give me 46, 6, 5, 6 over 6 minus 7, 29 over 6 is equal to 45927 over 6, which is equal to 15309 over 2. So our final answer is 15309 over 2. And if you had done this the other way, where you used the stars as placeholders and went back, then you would get the same answer. So it's really up to you and your personal preference, which one makes more sense to you, which one do you like doing better. Okay, and then I'm going to quickly go ahead and also do the last problem. I will, however, give you answers. So number 1, you should get 609 over 4. Number 2, we just got 15309 over 2. Number 3, you should get 7 over 54. And number 4, we are going to do together. So keep in mind those answers, see if you can get them. If not, we will talk. My computer's at 10%, so I'm going to hope that I really finish this problem quickly. All right, so we have the integral from 1 to e of ln of x quantity squared over x. So the integral of 1 to e of ln of x squared over x dx. I'm going to let u equal ln of x because I know the derivative of natural log of x is 1 over x, and I see 1 over x in my problem. So du is equal to 1 over x dx. Dx is going to equal x times du. So my integral is going to be, I'm going to use the star method for this one. The integral from star to star of u squared over x times, now my du is now, or my dx is equal to x times du, x times du. X is canceled, so I have the integral from star to star of u squared du, which is going to be equal to u cubed over 3. And then I know that u is actually equal to ln of x, so it's going to be ln of x cubed over 3 from 1 to e. And then I'm just going to plug that in. So I have ln of e cubed over 3 minus ln of 1 cubed over 3. The natural log of e is equal to 1, and so this is going to be 1 cubed over 3, which is 1/3, minus ln of 1 is 0, so that's going to be 0 over 3, which is 0, so I'm going to get 1/3 minus 0, which is just 1/3. No problemo. Okay, so that is all I have for this lecture. That is definite integrals with absolute value and u sub. You'll see a couple of those problems on WebAssign. I tried to do a little bit more difficult problems in this, so hopefully that helps you out. But please bring up in class any questions about other problems that you have in these notes or WebAssign, and we can go over those together. And if not, that's all I have. My computer's at 8%, so I made it, and have a lovely day, guys.